Okay, this was where we stopped. So I was saying that we know f of x naught, we know f of x2. But how do we get f of x1? So we got f of x1 from the step size or from the width. So the width is 0.4. So that's how we know that we need to evaluate f of 0.4. So simply put, so in a case where, let me do an example. Okay, so in a case if n is equal to 3, then you know that I said that you need f of x2, f of x1, f of x2 here, then f of x3. So the f of x1 you put here is going to be the result of what you got here. Then the next one is just going to be these 0 points, what you got here, then times 2. So I'm going to draw an example where you would understand better. So when we do all this evaluation, you arrive at these values. Then when you simply put it into this equation, you arrive at 1.068. And we know that the true value is 1.64. So when we track the error, we got about 35%. So the error drastically reduced with the use of multiple segments. And in this case, we just used 2 segments. So if we've used 3 segments, the error would have actually reduced much more than this. So we need a code in order to do it for us, because like we already know that if we use more number of segments, we are going to reduce the error. But in the case we have to use like many number of segments, we cannot be doing the calculation by hand. So we need a computer program that would do it for us. So in this case, I've written an Excel VBA code to actually do for the single segment first. So this Excel VBA code, the formula for single segment is given by, the formula for a single segment is given by this. Let me just drop it here. It's given by this. So this is a single segment formula. So I'm just using that question. I'm writing this. This function is the question. So this is the question we are giving. So this is the question. It's just in programming form. That's where this was written. Then the trapezoidal rule is given by this equation. So this equation in code form is given by this. So you have a b minus a here, then f of a plus f of b divided by 2. So this is the Excel VBA code to do that. Then for the multiple segments, this is the Excel VBA code for it. Yeah, for the multiple segments using trapezoidal rule, this is the formula. So you have this formula here. So let me bring it down here. So here is the formula. So simply put, this is the evaluation of the function at the lower limit. So h, we need to get h. Then h is b minus a divided by n, which you have here. Then this is f of a. So you need to get your f of a. And since you are summing over, you need a sum variable that will hold the summation. Then for this portion is f of b. So evaluating the function at the upper limit. So this is f of b. We added it to the sum variable. Then the value in between here is this particular value. So 2 times f of h. Remember I told you that what you get within this is f of h, but you have to multiply it by I because it's the step size. So for the first step size, you have this I. So I is changing from 1 to +1. So you have to keep on upgrading the step size. So this particular equation here is simply what you have here. Then this if block, this do loop is to do the summation from I is equal to 1 to n minus 1. Because at this point, if I is greater than or equal to 1, it's going to exit the loop. So it's not going to get to this n here. So if it is, that's why you have n minus 1. If I is greater or equal to, so when I becomes equal to n, is going to exit the loop. So that's where the -1 comes in, because it's not going to get to n. The summation is not to n. If the summation was to n, then this equal to will be removed. So this is the Excel VBA code to actually do it. So let me go to Excel VBA. So this is the Excel VBA in VBA format. Then this is for the single segment, and this is for the multiple segments. Then this is the function given in the question. And if you want to evaluate the step size, so I just wrote another function to evaluate step size. So we already have this equation from the note, b minus a divided by n. So you have b minus a divided by n. So you already have this step size. So in order to, the name of the function is trapezoid. The name of the function is trapezoid. So in order to call it, you just go to your Excel worksheet. So you go to your Excel worksheet. If I want to call it, I'll just say equal to trapezoid BA. So that's how to call it. So B on sheet 1, I've specified B as 0.8, then A as 0. So that's why I can simply call it using B and A. So when I click enter, so this was the value we got there. Then in order to, this was the value we got when we did the manual calculation. In order to get, using multiple segments, in order to call it in Visual Basic, in Excel, just say equal to trapezoid BAN. So on sheet 1, I defined n as 5. But in the work example, n is 2. So if I just put 2 here, so this was the value we got with that. So if I want to know the progression as, so if I put n here, then, and I put the integral at this column here, if I create a column, here, so I want to use trapezoidal rule to evaluate the integral when the step size is 2, when the step size is 3, 4, 5, 6, 7, 8, 9, 10. So all I'll simply do is to call this function. So equal to, then in place of n, I'll put a1. Sorry, a2, because n is in cell a2. So I get the value of the integration when the step size is 2. So for the other step sizes, to get it, I'll just do it this way. So you can see that in the notes, I think let me share the note. In the notes, the true value of the integration is 1.64. So a smaller, using more step sizes, we are actually approaching 1.64. So let me put 15, 20, in order to increase the number of segments, 30, 35, 40, 45, 50. So if I increase it, the true value is 1.64, so I'm approaching 1.64. So let me use 70 segments, then 100 segments, and let me see the results. So when it's 100 segments, I keep on, I'm actually approaching the true value. So if you increasing the number of segments would reduce the error, and you would finally approach the true value for the trapezoidal rule, for the integral for trapezoidal rule. Then because n is the number of segments, in order to look at the weight, I wrote a function that will do that. So I'll just call the function. The function is trapezoid n. So I'll call the function a is equal to, in place of n is a2, because a2 is where the number of segments is stored. So the step size for 2 segments, the step size is 0.4. For 3 segments, the step size is 0.667, or the width. So when you have 100 segments, the width of integration is 0.08. So this is the code that is going to do the integration for us. So let me go back to the note. So we've been able to write the code that will do it for us. So we can use another example. So this is our friend, the falling ball. So we have been using this model since the beginning of this course. So this is the model of the falling ball. So we want to, the velocity is given by this, and we want to get the distance moved. So we know that the integral of the velocity will give us the distance. So when we integrate this function here, we are going to get the distance, and we are asked to do the integration. We have to calculate the distance from t is equal to 0 to t is equal to 10 using numerical solution. So, and you can integrate this analytically. You can do the analytical solution to do the integration, but we want to make use of trapezoidal rule, which is a numerical solution. And we are given the exact value as this. So we can simply go back to Excel to write the function that will help us do that. So this is the velocity. So the velocity is given by this equation in code form. This is our velocity, and this is what we want to integrate. So basically, it is this. We want to use multiple segments because we want better accuracy. But we are going to use this function. It's just that in place of, here we have your f of x, which is a different function. But now is v, we have a different function. So basically, it's this particular piece of code, but in place of f, we are going to be using v because we defined a new function because we have a new function which is given by v. So this particular code here is to do the integration using the trapezoidal rule, but now you have a different function using v. And for v, you need t. So you are integrating with respect to the time. Then you have this constant here, which you need to include when calling it. Then this function here is basically the same thing as this function highlighted. It's just that in place of f, I'm replacing it with v here. I'm replacing it with the new function v, and I'm replacing it with the new function v. So that's just the difference between it because you have a different function. So when we want to call it in Excel, you just call it using the definition. So in Excel, I'll just go to equal to, before that, I need the different number of segments. So let me copy it. So these are the different number of segments. And let me paste it here. So this is n, the different number of segments. Then this is the distance we want to calculate. Then in order to call it, we'll just copy this. Then I'll just paste it in the Excel worksheet equal to this. So for this, I need B, A, N, M, and C, D. But in our question, the B, which is the upper limit, was given as 10. The lower limit is 0. Then N is in cell G2. So let me replace it with G2. Then your M and CD. So on sheet 1, I defined B naught as 10, which is the upper limit. Our A is the lower limit, which is still 0. Then our M is 68. Then our CD, which is the coefficient of resistance, I defined it as 12.5, which is the same thing given in the question. So we have the distance, that's using 10 segments, dividing the function into 10 segments. So increasing the number of segments will give us more accuracy. So when we increase the number of segments, we finally approach the true value, because in the question, the true value is given to us as 289.43515. So as we increase the number of segments, we actually approach the true value. So this is the number of segments, and this is the step size or the width of it. So as the step size increases, the width of integration reduces. So we have so this is the width here. So as the step size increases, the width of integration. So this is the formula to calculate the width. The width is simply b minus a divided by, or the step size, b minus a divided by n. So we have been able to solve this. So the trapezoidal rule is just, you're using a first order polynomial, using a straight line, but it's not so accurate. But in order to achieve accuracy, you have to increase the number of segments and reduce the step size. So another method is to use a second order polynomial to approximate the function. In the last class, I said that a second order polynomial, you need 3 points for a second order polynomial. So for a first order polynomial, you need 2 points, but the second order polynomial will make use of 3 points. So that's for the Simpsons rule. So here, in place of the function, we approximate it with the second order polynomial given by f of 2, 2 indicating that is a second order polynomial. Then from the last class, we, using the Lagrange interpolation, we derived this second order Lagrange in polynomial by this equation. So if you can remember this equation from the last class. So in place of f of 2, we just use this particular equation. Then we integrate from x0 to x2. The reason we are integrating from x0 to x2 is that this is our x0 and this is our x2, because you need 3 points. So the third point is in the midpoint. The third point is your x1. So you are integrating from x0 to x2, and there is a point in between to give you the second order polynomial, because you need 3 points to approximate. You need 3 points for a second order polynomial. So that's why you're integrating from x0 to x2. There's a point in between here, which is x1. And when you do the integration, you arrive at this formula. So if you want the proof, you can, how to get from here to here, you can just read the textbook. So this is called the Simpsons 1/3 rule. And the 1/3 came from this particular 1/3 here. So that's why we call it 1/3. So to estimate the value of an integral using Simpson's 1/3 rule, you need to evaluate the function at x0, which is the lower limit. You need to evaluate the function at x2, which is the upper limit. I need to evaluate the function at x1. X1 is a point in between the upper limit and the lower limit. And this point in between the upper limit and lower limit is just b minus a divided by 2. So in this case, the step size or the width is at the midpoint and is given by this formula here. So your x1 is simply your x of h here. So we know that our h is given by this formula. So replacing h with this formula, we arrive at this. So here is your width, and here is the average height here. So we're going to use an example now. So we want to evaluate the value of this function at using Simpson's 1/3 rule. So for Simpson's 1/3 rule, this is the formula we derived. So we need f of x0, which is simply f of 0, that's at the lower limit. We need f of x2, which is at the upper limit, which we already calculated previously. Then we need f of x1 at the midpoint. So the midpoint is simply f of h, b minus a divided by 2. So b minus a divided by 2 will give us 0.4, which is the step size in this case. And we've already evaluated it in the previous example as this. So when we simply put it into the equation, we arrive at 1.364. So remember that the true value is 1.64. So tracking the error, we have like a reduction in the error. So when we use the trapezoidal rule for 2 segments, we had like 40% error. But simply by using a second order polynomial, and this is just one segment, so we reduce the error to like 16%. So in order to further reduce the error, similarly to what we did in the trapezoidal rule, we can just increase the number of segments. So where n is the number of segments and our h is equal to the step size. Our h is equal to the step size. So we use the same formula. So now we are dividing the function into step sizes. So from x0 to, so this is this first step size, this is the second step size, and this is the last segment. So this is the first segment, second segment, then the third segment. Then you are integrating from x0 to x2. So like I told you, because you have 3 points, for Simpsons 1/3 rule is a third order, so it's a second order polynomial. And for the second order polynomial, you need 3 points. So the 3 points are x0, x1, and x2. But x1 is in between, but you are not using it. So for the next segment, you need x2. So you start from this point, x2, x3, and x4. But you're not using it within the integration. These are the midpoint. So till the last value. So the result of this integration is given by this. So when you simply we got, this is the formula we derived here. So in place of b minus a, in place of h is given by b minus a divided by n. So in place of b minus a divided by n, we just use the h. So the result of this integration is this. The result of this integration is this. Then the result of this integration is this, using the Simpsons 1/3 rule. Then when you combine the terms together, you arrive at this grand equation. So what this equation is saying is that if you want to use multiple segments for Simpsons rule, for Simpsons 1/3 rule, first of all, you need to get h. So we know the formula to get our h. Then we need to evaluate the function at the lower limit. We need to evaluate the function at the upper limit. Then we need some points in between the limits. And those points, in order to get those points, we need the step size. So we need the points at f, x1, x2, x3 until we get to xn. So this is saying that the odd points, you would multiply it by 4, then you sum it over. The even points, so you have 2, 4, 6, 8, you would multiply it by 2 and you would sum it over. So this is the formula for Simpsons 1/3 rule using multiple segments. So in place of h, replacing it with b minus a divided by n, we arrive at this formula. So one thing you should note is that the Simpsons 1/3 rule, you can only use it when n is even. That's when the number of segments is even. The reason being that, we're using a second order polynomial. We're using a 2-order polynomial. And a 2-order polynomial is even. And for 2-order polynomial, you need 3 points. So the number of segments you can have for 3 points is 2, which is even. But now you are using multiple segments. So, for a second order polynomial, you need 3 points, 1, 2, 3, to give you your 2 segments. To give you your 2 segments, you need 3 points to give you your 2 segments. So one thing to note is that the Simpsons rule, 1/3 rule, can only be used when n is even, because you need 3 points for even segments. You need 3 points for 2 segments, and 2 is even. That's what you should note. You cannot use the Simpsons 1/3 rule when n is odd. So n can only be even in order to use the Simpsons 1/3 rule. So that's just the demerit of it. So we want to evaluate this function using multiple segments Simpsons 1/3 rule, and our n is equal to 4. So we need 4 segments. So since our n is equal to 4, we need to get the step size or the width using this formula. And we got 0.2 there. So 0.2 simply means that you evaluate the function at the lower limit, which is f0. You evaluate the function at the upper limit, which is f of 0.8. Then in between f of 0 and f of 0.8, you need this step size to evaluate the function in between. So we calculated the step size as 0.2. So given the 0.2 we calculated, which is the width, so that means that the next step is 0 plus 0.2, which is 0.2. The next step is 0.2 plus 0.2, which is 0.4. The next step is 0.4 plus 0.2, because our step size is 0.2, which is 0.6. The next step size is 0.6 plus 0.2, which is 0.8. And the limit of integration is 0.8, so we stop at 0.8. So we need to evaluate the function at these step sizes, at the start of the limit, at the end of the limit, and within these step sizes in the range of 0.2, which is our step size. So 0.2, 0.4, 0.6. Okay, here's a question. Is the step size more like the intervals? Yes. Yes, you got it exactly. So the step size is just like the intervals. So if you look at this particular, so from here to here is the step size. It's just the interval. It's just the interval. So another way for step size is the width or the interval, like you put it. So we evaluate the function at these intervals or these step sizes. So we already know this. We already know this. So f of 0.2 is 1.288. F of 0.6 is 3.464. So the remaining, we already know it from the previous example. So we just put it into the formula. Remember, this is the formula here. So this is the formula here. Let me just put it here. So this is the formula. But in this case, in this question, our n is 4. So n is 4. So we are stopping at x4 because our n is 4. Then in between, we need some values here. So here is when n is odd, and here is where n is even. So you are starting from n is equal to 1. So you have f of x1 here. Then f is equal to 3. The next one is f of x of 3, which is here. So we multiply it by 4 because x1 and x3, 1 and 3, they are odd. So you multiply it by 4 here. So for the even intervals or the even step size, so you are starting from 2. J is equal to 2 to n minus 2. So you start from 2, that's f of x of 2. Then the next one is f of x of 4. F of x of 4, but f of x of 4 is the last one. And 4 minus 2, we give you 2. So it's only f of x of 2 you can have here. And because it starts from 2 and ends at n minus 2, which is 2. So you can only have f of x of 2 here. So this is the last one. F of x of n is 4, so you have x of 4 here. So these are the odd values of n, and these are the even values of n. So the odd values of n are weighted by 4, while the even values of n are weighted by 2. Okay. So there's a question: what if the interval is 0.3, or your limit is between 0. Will you stop at 0.06? F of 0.06. Okay, thank you for that question. To answer your question, to get your n is going to be given to you. So in this case, our n in this question is 4. So it's given to us. So based on that, using this formula, you will calculate your interval or your step size. So in this particular question, our step size given this formula is 0.2. So we have to start from 0 to 0.8 because this is our limit of integration, but in steps of 0.2. So we start from 0 to 0.8. Then the intervals in between is in steps of 0.2. Since the step size is 0.2, so 0.2, 0.4, 0.6, then the last one. So in this case here, this is the formula. So when for odd values of I, you multiply by 4. Then for even values of I, you multiply by 2. So here, you have your x, f naught, you have your fn. So in between, you start from I is equal to 1. So this is your x1. Then the next one is I is equal to 3. So this is your x3. So for this one, you start from x is equal to 2, which is your x2. Then the next one is it's supposed to be 4, but it stops at n minus 2. So you cannot reach 4. So you just stop here. That's why you have this here. And since we've already calculated all of this previously, so our f of x naught is 0.2. So our f of x naught is f of 0. Our f of x1 is f of 0.2. Our f of x4 is x of 2. Our f of x3 is 0.6. And our f of x4 is f of 0.8. So simply put, this is x naught, x1, x2, x3, and x4. So using this equation, just put in your x1, x2, x3, x0, sorry, x1, x2, x3, and x4. And after that, you evaluate the expression. We got 1.62. So when we track the error reduced significantly. It reduced significantly to 1.04 because previously, when we used multiple segments, it was 16%. Then this is multiple segments Simpsons Rule. We got like it reduced drastically. So to answer your question on the step size, let me go to another example here. So I will end the meeting now